Uh, Welcome, everybody. I'm Salvador Cordova. This is a hastily put together meeting on the Dirac Notation. So I hope this is broadcasting in the right spot. I'm not even sure where this is showing. I have a number of channels, and oh, there's Immutable Destiny.
Hey, what's going on?
Hey, how should I refer to you? Should I call you Immutable? Is that what people call you? Oh my goodness, Doki's here. What, Doki? This is really a dumb question. What channel is this?
Jesus.
I have so many.
Oh, Lord.
It's kind of embarrassing.
That's always the question you ask yourself in the morning. What channel am I on?
What channel am I broadcasting on? Hi, Doki. Goodness. Is this the Evidence and Reasons channel, or I have no idea what channel this is. That's embarrassing. Hi, Sal. Well, I'm not going to worry about it. So this is the this was a hastily put together meeting. Oh, the Salvador Cordova channel. Okay, whatever channel that is.
All right. Well, that's something.
What had happened is, just for our listeners, we're going to have this on my channel called the Evidence and Reasons Wild Frontier, and it just there were some technical problems. So what I need to do, I'm going to ask someone in the chat here. Doki, do you know Doki?
I do.
Okay. So Doki, can you give a link to? I don't actually have a link to my own broadcast. If you could post it, let's see if I can make you a. I can't make you a moderator. I don't even know what. Don't worry about it. I'm sorry for all the trouble, guys. I'm gonna search around. So I don't know if do you go? Should I just call you Immutable? Is that?
Yeah, if you want to. It's whatever you feel most comfortable with. I don't really care.
What do your friends call you on publicly?
Andy.
Andy. Okay. Well, we'll go by that, and I'm gonna continue to look around for where the stream is showing.
Oh, this is disappointing. I knew that my PChem course kind of cut out some of the mathematics on quantum mechanics.
Okay.
But
yeah.
They didn't even bother to show the derivation for how the solution to the Schrodinger equation is found. Oh, that's... And here they made us do Calc 1, 2, and 3 to actually take that course. God, that's annoying.
All right. So you have... What was your PChem book?
It was Physical Chemistry by Atkins.
Okay. My PChem book is Molecular Driving Forces. And I haven't read... I've not taken physical chemistry. And as you know, I've not even taken formal organic chemistry. I've only taken biochemistry courses. So
that when you first said that, I mean, that's astonishing, really. I mean,
well, let me say this: I went through 2 semesters using the Leniger textbook, and the guy teaching my course was the dean of the department, and what I said is, I'm going to take organic chemistry concurrently. And at the time I said it, that was the intent. And then I had to just bail out. And so that's how I got through the class. And I actually had a graduate level one on chromatin modifications. So yes, there were parts on the exam where they talked about nucleophilic attack, and just like, yeah, I'm going to punt on sections. But to the extent like where he said, okay, just draw a diagram of the citric acid cycle. The citric acid cycle, it's like, oh yeah, just easily do it. And he said, okay, just write all the chemical diagrams. It's like, yeah, I did that. It took a long time to just memorize the, I can memorize the diagram and recapitulate it. I didn't understand all the.
No, I think I remember the citric acid cycle is probably the thing I remember like the most amount of in terms of like metabolic cycles. and part of that's because like when I was taking Biochem 2, I had to take it twice. So I took it spring, but I was taking too many courses at the time, and I was just like, nope, fuck it, I'm withdrawing. And in fall, I retook the course, and the only way I could learn it was by like redrawing the thing like over and over and over and over and over and over again. Because,
yeah, that's so.
Yeah, because I remembered, I can remember certain parts of it, but it's a pretty short cycle, but there's a lot going on with it. It's like a series of like, what is it again? Like 8 chemical reactions overall, I think.
If I may ask I'm going to try to figure out, now that Speed is here, maybe you could talk to Speed for just a few minutes while I figure out what channel I'm broadcasting on, because I have no clue. I just slapped this together, kind of.
Yeah, I have no idea either. Let's see if I got both your channels up here, I think. So let me refresh them and see if I can spot one.
Let me load up my Griffiths textbook.
Okay.
Get that.
And let me get my Griffiths textbook. Okay, so to those who've actually joined us here.
I don't see you on either channel.
Okay, this may be on an obscure channel. Would that be funny?
Wow.
Well, so we're never going to be able to find it again?
Well, we're obscure people.
It'd be great if nobody watches this shit.
It says here you're under Salvador Cordova. And so let me see if I could find my Salvador Cordova email. And thank you for that. So if I can log into the right email account, I can straighten this all out. So I apologies for all the problems I caused, gentlemen. And hopefully,
we expect nothing less from a creation.
Oh, that's right.
So
there's a lot of Salvador Cordova channels. Unfortunately, you are not alone.
There's a guy in jail.
Oh, there you are. Oh, Dirac Notation. Yeah, you're on Salvador Cordova. Cool.
I didn't even know there's a channel called Salvador Cordova.
Yeah, I think I got one for my email, so my name. Ooh, I'm getting rid of the audio on this thing. So you got Doki Doki Bible Club here and a bunch of other people in chat?
Yeah, they found me. I thought this is gonna. Well, thank you all for being a part of the channel. Just so now we'll why don't one of you describe what we're going to try to do today for our audience?
Well, I think we're about to perform a miracle, because quantum mechanics takes nothing less mathematically to work. At least if you ask me, because I haven't taken partial differential equations in about 2-3 years, so it's going to be interesting.
That's just, don't you just come up with like, what the hell they call it? What do they call it when you break an equation up into 3 parts?
It's called separation of variables.
No, well, it's something else. What do they call it? Shit. I don't know.
What I always say is that physicists invent fancy terms for terms that don't need to be fancy.
Well, there's a mathematical term for it when you, it has to do when you're dealing with cosines and crap like that. We're not live, are we?
Well, we are.
We're live. We're live.
We're live. Oh shit.
Well, all right.
Hi, public.
Okay. All right. Don't sweat it. This is why it's not on the Evidence and Reasons channel, I hope, because that's for the homeschool moms. And so I learned things the hard way. Oh, let's see. I may have found the right channel. So see if I find it here.
Will reload and work.
I got a link to it.
And if I don't find it, we'll just go on to business, and I'll take responsibility for having made a mess of things here. So anyway, thank you for all our loyal 31 subscribers that have found me here. And this is the Nerd Nexus. We're going to be talking about Dirac notation. So this is not anything immediately for discussions about creation, evolution, and creationism. So,
So, do
this
we want to
is-
go over the Schrodinger equation first, or just
yeah,
dive
yeah.
into
So
the
this is mostly to learn basic quantum mechanics and I've learned it mostly through the Schrodinger equation as it related to chemistry. So I have my Griffiths textbook. What edition do you have, Immutable?
I have the. Let me check now. It is the 3rd edition textbook.
I have the 4th edition. I'm better than both you guys. And
I have the 2nd edition.
Well, there we go. It's a numerical sequence. What do you know?
I got a live kitty on the front and a dead kitty on the back.
Well, that's the whole thing, you know. That's Schrodinger's cat there.
I know.
I like the live one. And the cat there, that one looks so peaceful. He looks like he's just, that's just the cutest picture. So,
it is a rather nice picture.
I got a better kitty on the front. Oh, I got 3rd edition, I guess. Okay, I'm sorry. So I got third.
All right, Speed. I guess you want to show off. God damn it.
Yeah. Well,
okay.
Okay, so there's this particle in a box thing.
Yeah, there is.
And I'm gonna show it because that's actually how I was. It does relate to the Schrodinger equation. And so they have this, and you're the chemist here. You could help us through. There's this Pauline conjugate.
Pauline carotene.
Yeah. So let me find where they actually begin deriving the solution for the Schrodinger equation in this book. I really don't care about anything else. Hello, come on. Time independent. Okay. Is it actually going to show me, or is it going to just be annoying? There we go. So, wait a minute. Yeah, good thing this is not on the Evidence and Reasons channel, because this is kind of being annoying. Let's see. Okay, physical interpretation, yeah. $17, yeah, okay. Where is it actually going over how to solve it? Give me a minute.
In Griffiths?
Yeah, it should be, 1 second.
They're a little bit cagey.
Yeah, I'm trying to find where it actually goes over solving the Schrodinger equation itself. Or is that left as a problem?
So, well, this is actually good. This is good to be talking about it. So I'm going to show the very simple case because it's like the particle in the box. This is like the simplest case.
Oh, here we go. Found it.
So we have this beta carotene conjugated Pauline, and supposedly it approximates a particle in a box. So you just get that nice little sine wave here.
Do you have a picture of that thing, or can you share the screen?
Let me show it. I'm sorry, I can't. I keep forgetting sometimes I don't have my screen shared. So this comes from the Wikipedia article on particle in a box.
Okay.
And so a lot of you could see they don't actually use a lot of Dirac notation to solve the particle in the box. And so this is how I learned. This is how I studied quantum mechanics. So there's not one lick of Dirac notation to describe the solution. So they say, okay, what's the closest thing in nature? It's not a very good approximation, but it's about the best example. Is this beta carotene conjugated Pauline? So
the reason
I don't know if it means that the electron is trapped in between the N terminus or C terminus.
So if you click on the picture, right, enlarge it a little bit. There we are. Beautiful. So if you see the double bond on the ring, right?
Right here?
Yeah, on that ring. Actually, let me draw that for a moment. And then share my own screen
Okay.
so that I can show what's going on with it. Because, yeah, that's actually an interesting way to kind of depict the particle in a box for chemicals. There's simpler models you could probably use, but that's certainly a decent one.
Oh, is that a pi bond? Is that the pi bond?
Yeah, it is.
Okay.
And that pi bond can resonate over outside of the ring and move through that system. If I can draw this molecule, that'll give me a lot.
Okay, I'm going to stop my screen share.
Yeah, screen share for the time being because I need to copy the molecule down on the tablet.
Oh, that's right. We'll just talk, and I'm going to click around. Okay, I'll screen share it. You let me know when you want to.
Yeah. 1 sec.
Well, I want to thank everyone who's joined our Nerd Nexus. This is showing the world who the real nerds are. Yep. Coming on a Friday night to talk about quantum mechanics and chemistry. Yeah, you're serious guys, man.
No, yeah.
I want to say a special thank you for coming because you said something like you couldn't pee straight when you get this late in the night or something.
Yeah.
Sorry, I didn't.
Yeah.
Yeah, we're almost there.
I'm really. It means a lot to me. You came and joined us because you're the life of the party, man.
Let's see. That's that. Another one.
Let's see. So I was showing the beta carotene, and there was one other thing. Oh,
so
now
what
I know.
Page number was that in?
They don't show beta carotene in the Griffiths textbook.
Oh, they don't. Okay, this is something else. Okay.
Yeah.
Well, a particle box. It is the. Let's see.
Okay, carotene. 1 second.
Oh, I just figured out what account this is coming from. And
well, that's rather being kind of some.
I just figured out the account. I finally figured it out. I feel so good now. It's from my. Yeah, I know now it's nice to know where you are. And because I would have lost another broadcast because on this channel I had one talking about space aliens. I interviewed James W.
Oh, really? So, that's interesting.
Yeah. He argued, he was modern day debate arguing for the authenticity of alien abductions and UFOs.
Yeah, here we go. Let's see.
All right. Want me to stop sharing my screen?
Yeah, a few more seconds. I had to pull up the molecule again to make sure I had it, have it almost drawn right. Let's see. And almost there. God, this is a long molecule. Sorry, this is. Stop it.
I was pretty excited about alien abductions until I heard about the rectal exam.
Yeah, me too.
Yeah.
About the what?
The rectal exam.
Oh.
Yeah, I didn't like that so much.
No, not exactly the way you want to end a day, is it?
No. Not the way I want to meet an alien. I thought a handshake, they had to be a handshake. Anyway, a little humor for yourself. You can download this video and, edit it and upload it to your channel or
actually,
whatever.
You know what? It's not important to have the beta carotene necessarily as the molecule of interest. I can just explain what the particle in a box is about without it.
Right. Exactly. I guess the point is that I wanted to say there was a real world. There's a real world example of the thing in our textbook. So I didn't answer Speed of Sound's question. What page is the particle in a box? It's actually in my version of Griffiths. It should be really early on.
Yeah. So, let's see. Is my screen sharing?
Sorry, I was negligent.
No, you're good.
Yeah, and I'll make it nice and big for everyone to see.
Great. Let me zoom in a little bit. This is going to be Kind of
Some
interesting.
operators.
So the particle in a box situation has this following depiction. So imagine for a moment that you are encased in a box of side length of length L, and so this is L, and this is minus L, and that essentially what we are imagining is we are imagining some particle that is placed in this box, and we would like to know, assuming that it's moving with some momentum, or with some velocity rather, what is the motion going to look like for the particle in the box under the assumption that at negative L, the energy here is infinity, and the energy here at L is also infinity. So that's basically what it's doing. So the representation of this is that after some point in time, right, this particle is going to move, it's going to move, it's going to move, but it's going to be repelled again by this energy, by this insane amount of energy put into the system, and it's going to be repelled. So does that make sense so far? Or
Yes.
good?
And then I'll also,
Okay.
I also wanted, that's why I wanted that physical example.
Right.
The beta carotene, because just imagine that the sides of the wall here are kind of the, I presume, kind of the.
Let me use an example that's
the limits where the electron could reasonably be. Granted, this is an approximation, but the idea is there's some sort of strong limit where it's very unlikely the electron's going to be outside. So if we have a pi bond, it's going to be really it's going to be constricted to this area.
Yeah.
And the nice thing is this is a nice one-dimensional case.
Right. Let me give an example of my own. It's not going to be the same one, but it's comparable. Yeah, that's fine. And let's do it so that it has.
He's trying to draw a benzene ring. Oh. Purine. Nope, something else. Those supposed to be hexagons?
Those are supposed to be hexagons. Actually, I drew that incorrectly because I don't want that to be there. I want this actually to be this is a little harder than I anticipated it being, but let me see. Let me get rid of that. Okay, so I want one between that, and I want it to be so I want it to be a hexagon. I want the electrons to be here, and I want it to be here, perhaps. And perhaps I'll have a set of electrons that are here. So with this molecule, right, what we can see is that there's two hexagons, and there's a carbon that's bridging the two, and that the flow of these electrons, in some sense, is restricted, because the only resonance that this can have is if this pi electron migrates here, for instance. Well, this carbon right here, if that happens, right, this carbon is making 4 bonds already. So it's making 2 with one here, and then 2 because of the pi bond. But if this pi electron migrates over here, what's going to happen is it's going to create 5 bonds, which carbon cannot do. Carbon can only support 4 electrons. And that's going to force these electrons to push here. But this would mean that this center right here would have 5 electrons. And so that means that this poor pi bond here would have to migrate to a new, would have to migrate somewhere else. And so what it would look like, it would be 1, 2, 3, 4, 5, 6. And we have that. And we have that. Now I have 1, 2, 3, 4, 5. Now, hold on. Sorry, sometimes drawing can be a little more challenging than I expected to. 1, 2, 3, 4, 5, 6. That's going to have to work, even though it looks a little strange. And here. Right? So does the explanation make sense in terms of the arrow pushing and how, why the pi bond has to move?
So the electron moves, or the pi bond?
So
some pi bonds does that mean that the pi bond is not always in the same location between the carbons? The carbon, is it like a resonance structure? Is that what they call it?
So this
is a resonance structure.
Right. So what this means in essence is that this pi bond, right, because it has, so this pi bond has a pair of sigma electrons and a pair of pi electrons. And it means that these pi electrons here that are contained within the bond, these pi electrons, as it turns out, are moving from the bond between this carbon and this carbon, and they're migrating to the bond between this carbon and this other carbon.
So that means it could actually travel, like in the case of the Pauline, it could travel all the way from from the N terminus to the C terminus.
Right. That's correct.
Wow. That speed, don't you think that is just like totally cool?
Yeah. And so this is actually kind of characteristic of a particle in a box, because in this example, what we're essentially illustrating is that there are electrons that are housed somewhere. They can only move in a certain direction. And otherwise, for instance, if this pi bond were to break and you generate a plus or minus charge, that actually won't happen because it requires too much energy of the system. Right, so it's going to move the pi electrons around like it did in this case before it breaks apart into a plus and minus charge. So with that kind of illustrating what the particle in a box is about, the particle box being about how electrons can only move in certain are confined by energy barriers that govern their motion. Let's first, before we talk about the Schrödinger equation, let's first talk about the following differential equation.
Yeah. Immutable, could I just pause a little bit? Just briefly. See, the reason I liked seeing that, what you gave, is that a lot of people are just like, well, what's this talking about? When I actually kind of see it as a physical thing, then I don't know, it just seems to resonate a little bit more.
Yeah.
So when we have, if I could just, could you unshare your screen briefly? And I'm going to go back to the Pauline.
Yeah, sure.
Which I just as quickly lost. Oh goodness, let me try to bring it back up. So particle, it just does something when you could see that it's trying to describe something physical, because if I can visualize it in my head as something physical than something purely abstract, then I don't know that I learn it a little better, because then I have something to conceptualize. So let me see now. I'm going to try to share my screen. Thanks for letting me pause a little bit, because this helps me talking through it. So when we have this polyene, this beta carotene here, we can actually imagine then this pi electron going back and forth here, like the particle in the box. So there's a probability. I'm getting ahead of myself. There's going to be a probability that the electron's going to be here more, or here more, and not so much kind of in the middle. Definitely not at the ends. And you're going to show why that is from the Schrodinger equation.
Yeah. And
okay,
actually,
so take it away.
And actually, let me give one last example of a particle in the box.
Yeah.
And it's
So,
probably...
let's go ahead and share your screen. Thank you.
Yeah. Let me give one last example of a particle in the box. And actually, this gives rise to a very interesting realization for people that have taken Orgo 2. So, for instance, let's just consider the simplest, perhaps one of the simplest aromatic compounds of all time, if not the, which is benzene. So benzene is a 6-membered ring and has 3 pi electrons. And essentially, the only thing that this thing can do in terms of resonance is this pi bond can move here, which in turn causes this pi bond to be pushed up, to be pushed in the ring again. Whoops, is it not wanting to? Oop, went too far. No. Okay. I love it when technology chooses to work.
Now, do you tutor chemistry still?
I do.
Do you use this to draw diagrams to teach your students?
Yeah, I do. Luckily, thank God. So this pi electron can move here, which would cause this pi electron to move here, which would cause this pi electron to move here. And so you get a resonant structure that essentially looks identical, but it looks that this goes there, that goes there, and that goes here. So
how did they figure that out? That's really cool. I mean, that they could detect that. It's amazing.
Yeah, that's and actually one of the interesting things you'll notice is that let me remove the arrows because it kind of complicates things now that I don't need them.
Was that Kekulé was on a bus or something, and he was like sleeping, and he dreamt of monkeys forming a ring? That's how he came up with the benzene ring. You remember that?
That's probably correct, but I don't know.
Yeah, that's the story about how they figured out the resonance structure of the benzene ring. He actually had a dream, and he saw these monkeys all joined together and saw them zipping around in a circle, and he thought, it's resonance.
Oh, there we go. That's one way chemists have figured something out. I mean, person figured out they had LSD by tasting the damn thing, so
yep,
won't surprise me. And so what's curious about this, you'll notice, and actually let me perhaps redraw these pi bonds in a different color. Whoops, that's not good.
Ooh.
Fine motor control, fine motor control.
Nice.
Right, so that's there. And what you'll notice is that these electrons are in fact in a different location. And if I draw the electronic structure for what exactly this thing looks like, which not always the simplest thing to understand, but it looks like this. So we have an orbital, an orbital, an orbital, an orbital. And what you have here, for reasons I won't go into, is you have conjugation between the electron-rich portions of this orbital right here. So this is the electron-rich portion, or actually, sorry. So these top nodes here are regions where the density of finding that pi electron is rich, and that's true for each of the ones that are facing up. And the probability is low where these orbital lobes are facing down. And as a matter of fact, so let's realize something, that each of the carbons in this structure have the exact same what's called hybridization state. So it means that they're housing the same number of electrons in the same type of way. And this is called sp2 hybridization. Because one of the properties of a pi bond is that pi bonds, the geometry is 180 degrees.
So the molecule is planar?
Yep. So because they're planar, so because each of these orbitals are planar to each other, something interesting actually happens in that the electron-rich region that's here actually engages in a type of partial donation of its own electrons to the structure. Oh, I'm sorry, I missed a orbital. And that's red, and this is blue.
Andy, I got a question.
Yeah, one
really
sec.
Basic So this is like what you drew with the blue and red. Are those p orbitals of some sort, but they're modified?
So what this is, so these, so what I'm drawing here is actually an example of what's called something called hyperconjugation. So,
okay,
hyperconjugation. And this occurs when the electrons in an orbital, when the electrons in one part of an orbital are essentially attracted to electrons that are, or are attracted to something partially positive in a less strong orbital in the same molecule, if that makes sense.
So when you say molecule here, is it like a carbon, electrons in one carbon being attracted to electron, a kind of a positive region in another?
Yeah, so what I mean in this case is that, so remember how I said that the red parts of these are
okay,
electrons?
I see it now. Yeah, yeah, your diagram actually makes it clear. All right, so
yeah,
yep. Thank you.
Yeah, the red parts are electron rich. The blue parts are electron poor, and because of that, there is a type of sharing in electrons between the between those richly electron charged areas and the less richly electron charged areas.
And just to, and I'm sorry to interrupt you, but just because I'm a little stuck.
Yeah.
Really, if we could solve the Schrodinger equations, if we at least did it computationally, you could actually see that. This would be a solution. Okay, all right, thank you.
So, as a matter of fact, what you would see in a diagram, right, if you were to visualize this as kind of a geometric object, and this is kind of the fun thing about aromatic objects for this reason, is that this object, in fact, would look like this. Actually, in fact, let me redraw that a little bit. That, and let me draw
the old circle.
And the reason it's drawn like this is because, notice, even though my diagram isn't the best, that every part of this molecule, so every negatively charged region, is sharing its electrons with a region that is not negatively, that is electron poor in density. And as a result of that, because we're doing it in the exact same way, the distribution of electric charge and electric density around this molecule is even. It is symmetric everywhere. And the more important thing is that, like what we were talking about, the particle in the box, these pi electrons, unless one of the bonds breaks for some reason, cannot go beyond the confines of this molecule. They cannot go anywhere else.
So it is like a particle in a
particle in a ring, perhaps.
Particle in a
particle in a ring or something.
Right. So it's not exactly a one-dimensional case. This is going to have to be like a kind of a two-dimensional trap. So
yeah,
we'd still be the Schrodinger equation, but then it's going to be a little bit more complicated because we're no longer dealing with the one-dimensional case. But that is really cool.
Yeah.
So there's a probability then that the electron inside the benzene ring, that it'll have a certain distribution.
Yeah. So to go on to the actual Schrodinger equation, let me write
Can I ask one other question? I mean, with your understanding. So when we collapse if we were able to hypothetically make I thought I saw like this quantum microscopy or something, mm-hmm. where they could kind of measure the location of an electron. Yeah. So if we're actually taking snapshots of the locations of these electrons, we're collapsing the wave function just briefly, just so we could see where, we make it real for just a brief moment and then we kind of let it go.
Yeah.
That's my understanding. So I really wish I had that video. They had a video when I took chemistry where they had an experiment. I don't know how they did it. They might have done it with like x-rays and then they do inferences and then they can plot the position of the electron when they measured it. And then over time it would plot. So they actually had to collapse the electron several times, but then let it go and uncollapse it. Okay. That's the way I understood it. So I'm not out in left field for saying that. Okay.
No, that's perfectly fine. So before we actually solve the Schrodinger equation, let me introduce the type of differential equation that we'll have to solve. And I'll write it as x double dot, or as x double dot is equal to negative k squared.
Negative what squared? K squared.
Negative k squared x. And Sal, please tell me you remember how to solve this differential equation.
It's a sinusoid. That's a spring.
Right. So this actually, if you, for those of you that haven't taken calculus, there are exactly two functions that satisfy this. And that is an arbitrary function or an arbitrary constant. Well, in this case, assuming x is a function of some variable, say x is a function of t, equals cosine of t. Well, an arbitrary constant times cosine t. well, of k times t in this case, rather. Plus b times sine of kt. Good.
Well, I wouldn't have. It's just because I recently touched on this that I knew it, and because when the professor was giving us this, he tried to give us the easiest differential equations.
Right.
So this is, it's nothing like the spherical harmonics. So
no, and thank God we're not doing that today. That's going to be, that's a different subject. But so let me essentially, well, I might touch on the three-dimensional case, but for now, let's say what the Schrodinger equation actually is. So the Schrodinger equation says that psi, and I'm going to use dot notation for derivatives, and it should be noted that, so let me make a note for those of you that are wanting to be technical. X dot for physicists means that this is the first derivative with respect to x of some function, right? In this case.
can I ask? We don't in Griffiths it uses partial derivatives.
So partial derivatives are when we're dealing with multivariables, but
Okay.
in this case, we're considering the one-dimensional case.
So
all
right, just because both Speed of Sound and I have the Griffiths book.
Yeah.
What we would do then is we could still say partial of this. We could still say, let me see if because I have the book here. We could still say dot. So where it says like equation 1,1 in the second edition, we could use the psi
double dot.
It only has first derivative. It would be psi dot. I don't see psi double dot. Psi double dot is with the x, would be the x variable.
Hold on a sec. Let me check that, because I might be incorrect. Let me see now. Oh, yeah, that's because it's dealing with the time-dependent Schrodinger equation.
Okay, so we need to go to the time-independent Schrodinger equation. Okay, so let me look that one up.
Yeah, I don't think this one actually mentions it because it's kind of trivial to solve, but a simple Wikipedia article will do.
Okay, so there's a simple harmonic oscillator, and see, this is so this is actually the challenge sometimes is knowing the various versions of the Schrodinger equation, and then also sometimes just being able to deal with the slightly different notations. And so I'm just trying to square it, pun intended, with
interesting.
With what's in the Griffiths textbook.
So this is the general form of the Schrodinger equation. So
yeah, that looks the same as equation 1.1, except he's using that double dot notation for the second derivative of the wave function.
Yeah.
Okay, so is this time independent version?
Yeah, we're going to solve to the time independent.
Okay, all right. If I could just time out here. The engineers almost never use dot notation for
they prefer prime.
For the x. It always has to be time. But I'm okay saying if we're using the dot notation for x. So
the only reason we're using x for the time being is because this will represent the position of the particle. And once we introduce time into the equation, we need that to be variable to be t.
So okay, I'm looking at this equation 2.5 in my Griffiths it
Mhm.
uses the partial derivative. It's like d. Do you have what does I
I
don't
can.
know how to show this on my screen. Can I just show it on my screen briefly to
Does
see
it look like? Does it look like this, for instance? Let me see if it does.
equation 2.5 in the second edition?
I think it might read as this in that case if you write it
It says
fully.
minus h over 2m, and then it has d squared psi is the numerator, and then dx squared in the yeah. Is that the same thing? I just want to make sure we're on this.
Yes.
Plus
Okay.
nu times plus v psi. Whoops. That's supposed to be a psi. Plus v psi equals e psi.
All right, we're cool. All right. I'm not, a little change in notation can just totally throw me off. So thanks for
No.
bearing. I appreciate it. So
So
same thing. Okay.
right. So these two are the same thing as each other. Great. Now, what we're going to do for the for very, very simple sake of argument is that for a moment, so what this V means is that this V of psi term refers to what's called the potential energy.
Is that new or V?
V. Nu looks like this.
Is it new? Okay.
Nu looks like that.
Sorry.
No, it's fine. So this is potential. So any potential energy that's contained within the system. For the moment, we're going to assume that this particle has no such potential energy. That's to say that the nu term, or the V term, goes away.
Okay.
And what that boils us into is that, I actually need to specify specify what this actually means. And if you go to the Griffiths book, what it'll tell you is that the appropriate boundary conditions to place on our differential equation are that, give me a moment, are that it should name them. It's not though. Let's see. Why is it being annoying?
What are you looking for?
Oh, wait, might be it. I'm looking for the initial conditions on the function.
Oh, well, if it's time independent, they're not really technically initial conditions. They're just constraints.
Yeah, that's another. Yeah, I use those two interchangeably, even though they're probably.
I guess the term is boundary conditions. So time t actually is not existent,
Yeah,
which makes
here
it
we
nice.
go. Here we go. So what we're going to do is that we're going to create the boundary condition that. So for this equation, we're going to make two assumptions. We're going to make the assumption that psi at 0 is equal to 0, and that psi at the value of L is also equal to 0. And the reason for us doing that is when this function, it's impossible for this particle to actually rest, say, here on the point L, because there will be an infinite amount of energy, and by definition, it can't move further, and it'll be forced to move back. So at the point L, this particle cannot be found. And at psi 0, we're going to assume that that the initial position when we start trying to trace the function, that its initial position at 0 is in fact 0. Good. And so under those set of assumptions, we then say that this function, that this differential equation becomes negative h squared, or not negative h bar squared, sorry. That negative h squared, oops, negative h squared divided by 2m times psi double dot equals 2e times psi. Well, let's notice something about that. We remembered that that psi double dot is negative k squared x, has a solution that psi is equal to some constant times cosine plus b times sine. So far, so good?
Yes, because I'm following it in Griffiths. That would be the classical simple harmonic oscillator equation.
Right.
And that's the general solution. Where I've always, even when I was taking the class, got hung up was when they try to solve for B. So
okay,
I'm reading it. So no, this is actually really good review that we're going through this.
Yeah. So in a moment, we'll reach that point. But so let's multiply each side by 2m by negative 2m over h bar squared, or over h squared. And this gives us that psi double dot is now equal to e times 2m divided by h negative e over 2m times h squared. Well, that means that times psi, sorry. And this means that psi is equal to, let's see, it could be, well, actually, let's think about this, right? So the term we have here, this is our k squared, right? So that means that k
is the square root of
yeah,
2me over, and I'm just reading this from the textbook. I wouldn't have deduced that. See, that's the thing, is these are nice kind of conventions that kind of help.
Yeah, so this means that this is equal to the square k itself, or yeah, that this constant that's going inside the cosine that's multiplied by x is, for our equation, the value of 2 times square root of 2 times m times e divided
Over
by
h bar.
h bar. Okay, might have been me.
Sorry, going to be anal here.
That's fine. They are important. They are different constants, and they do have different significance. Okay, that solves that problem. Now, our solution to this function is some arbitrary constant times cosine of square root
Where are you writing?
over h bar times x.
Are you writing somewhere and we can't see it?
I'm sharing screen. Is it showing up?
Oh, yeah, now it is. Yeah.
There we go.
Oh, there you are. Okay.
So plus another arbitrary constant times the sine of square root 2 m e over h bar times x Good. So let's box this away for a moment. We don't need to deal with it. Now, what we need to do is impose. What we need to do now is we need to evaluate this under our initial conditions. So we said psi of 0. So we said psi essentially of 0 is 0. So this indicates that what this means is that when x is 0, the value of y is 0. So when psi at the value of x is 0, y at the value of y, the value of the function is also 0. Make sense? This notation.
Okay.
Sal, so far so
That's the x coordinate, correct?
Yeah, this part here is the x coordinate.
So looking at the Griffiths diagram, the box has the length of a, and it goes from 0 to a is the coordinates of the box where the particle is.
We've chosen to call our box L in this case.
Okay.
So it's a semantical difference.
Okay.
At this point. And what we will now say.
I just want to say, if I didn't have Griffith's book, I would be totally lost at this point. But this is really good review. So thank you. And I got to tell you something. I gave up watching Nephilim Freeze debate just to be with you tonight.
Nephilim Freeze debating.
You're a heartbreaker. You know that?
Who's Nephilim debating and where?
On SFT's channel.
Oh
See what I've given up for you guys? This is how much you mean to me, Immutable.
I know, Sal. If only I could become a creationist and join you further in your insanity.
Okay, that's like giving up root canal to be here. Watching Nephilim Free.
Yeah, you're damn straight on that one. But so, okay.
Okay, so at L, it's also 0.
Right.
By assumption. Okay. So basically, this is kind of saying what parameters the sine wave can take.
Well, not just the sine wave, but the general wave function itself.
The sine plus cosine. Okay, thank you. The general wave function. Okay.
Yeah. And so, actually, as it turns out, if we plug this in, right, the first equation we generate is that, well, at x is equal to 0, 0 times anything is 0. Or, yeah, and the cosine of 0 is 1. So 0, because that's our value of y. So 0 equals, cosine of 0 is 1. So a times 1 is a. Plus b times the sine. 0 times anything is still 0 because this is a constant, this term here. Well, sine of 0, because of the way the sine function works, is 0. And this is 0. So, in fact, what we get is, because b times 0 is 0, we get that a equals 0. Okay. Now, that actually informs us that this tells us that psi, if a is 0, right, this means that this coefficient that belongs to our cosine term vanishes. Well, and the cosine itself vanishes because 0 times any function is still 0. So what we in fact have is that psi is equal to some arbitrary constant times the sine of square root 2.
Shouldn't that be a sine?
B, right? Because we've called a the coefficient or cosine.
B is equal to 0.
B sine.
No, A is equal to 0 because
Yeah.
Psi 0 is equal to 0 equals B. If psi 0 equals 0 and psi 0 also equals B, B equals 0.
So let's run through this again, right? The x, so when we plug in our equation, right? So when you plug in x, the cosine function evaluated at 0 is 1, right?
Correct.
So A times 1 is A, which we have right here, plus B times the sine of 0 times some constant, which will be 0. But the sine of 0 is 0, right?
Oh, wait. Can we hang on just 1 second? It has A times sine 0 plus B times cosine 0 equals B.
Yeah, we've chosen to change. We've chosen to change the order of our coefficients.
Okay, now what is it in your textbook? Just out of curiosity.
It's the same thing. It's the same thing, but when I wrote down the solution, I wrote the cosine, the letter A for our cosine and the letter B for our sine.
Okay, thank you. Apologies. Now,
Yeah.
we're cool now.
Okay. All right. So far the logic makes sense, right? Of how we got this.
Yeah. So now B is the arbitrary. Okay.
Yeah. B sine.
So I just okay. So speed of sound. This is the notation is just a little bit reversed from the textbook in the second edition.
Okay.
So if you look at equation somewhere between equation 223 and 224.
Yep.
The A's and B's are switched from what we're seeing here.
Okay. Yeah.
Okay. But so what we have now is that because B is, or in our case, because our A value was 0, so because this term for A was 0, we get psi is B times some arbitrary constant. Well, is some arbitrary constant times some sine function. And now we can actually involve our second initial condition. So our second initial condition says that psi evaluated at the point of x equals L, it causes this function to be 0. So that means we get that 0 is equal to d sine, or b sine, of square root 2m times e divided by h.
H bar.
H bar, yeah, sorry, H bar. Times x times our value of x. And so what this actually is interesting. So what's curious now is that we need to consider at what values what values is the sine function allowed to be 0? So the sine of 0 is 0, but that's an obvious solution to the problem. So what we will instead do is consider the sine of some integer times pi, which also, by definition of the sine function, is also 0. Well, what this means is that our function here, so square root 2 me over h bar times x would have to be Actually, wait. Excuse me while my mind stops working for a moment. Yeah, okay. Hold on.
Actually, there's a diagram. Figure 2.2 shows it.
Oh, here we go. Okay, good. Yeah, got it. Okay. So what we have chosen to call so is equal to n pi. So this means our value of x actually, wait a minute. Let me see how this book explains it and make sure I can explain it properly.
Can you page one picture over? Are you able? I like pictures. That's simpler for me.
Okay, here we go.
That one at the top. Figure 2.2 in your book. It's also the same one in my edition. It's easy to visualize. You could see that it's 0 for each of these waves.
Right. Let me move back to the other page for a second. I want to see its explanation for it.
Oh, Leophilius just wrote me. I thought I gave him a link. He can join us. Hang on.
Oh, okay. Got it.
Can someone write? I'll write Leophilius. He just wrote me.
So
I don't know. Maybe I forgot to include him in the email. So if you'll give me a moment, because I'm gonna forward the link. I feel really bad because I was gonna.
right. So this means that our value, so the values we need to have for so essentially aims that. Yeah.
Let me just forward Leophilius here.
I'm trying to figure out what I went wrong here. If I did go wrong.
Leophilius.
Oh, here it is. Okay, got it. Okay, right.
By the way, how did you get? Are you reading from a Kindle? How are you able to get the book on there?
PDF.
Oh, I didn't.
I would be in trouble if I told you currently.
No, just
yeah.
I'll drop that. Okay.
Yeah. That's why. So our value for L, right? Because we said that psi evaluated at some point L would have to be 0 according to this. And that means that that our value of L would have to be some sign of, if L is 0, that's fine. But if L is not but if L is not that, right, it means that if L is not 0, the only thing L can be is n pi. Great. Now, that just means that the solutions, if we remember calling this K, that our values of K times L would have to be n pi. And that means the value of L would have to be n pi over K. And I'm trying to see where exactly.
Let me see if Leophilius is trying to join us. Oh boy. Leo, you there? All right. Go on.
Good.
Sorry about that, Andy.
No, you're good. So, in fact, our solution's still, and it depends on the problem we give it, but our solution's still that our psi in terms of x is b times the sine of some constant k times x, but we actually know what this will be in this case. Right? We knew that that k and that our k is n pi over L. This also means that k and now what we need to do in one property of the wave function I'll introduce is that the probability of finding this. So if we consider this to be the probability and this to be the location, what must be satisfied by some wave function, however it looks, is that the probability everywhere, is that the probability over all space for this wave function. So that's to say, of the magnitude of the wave function, which we'll call psi squared. Magnitude of psi squared dx must evaluate to 1. Well, equivalently, what that means for our particle in a box, we don't actually need to consider. We don't need to consider all of that. What we just need to consider is.
Wait, hold on. Whoa, you guys have been live for an hour already?
Yep.
I thought we were starting at 9:30.
Eastern time.
I did too. But
are you in the flyover zone time zone?
No,
I'm sorry.
okay, the center of the
pretty much covered
universe.
everything?
Huh?
Have we pretty much covered everything?
No.
Oh,
No. We're just.
If like you guys are getting close to like wrapping up, then I can just go watch Nephilim Free get absolutely demolished by an actual nuclear physicist when he tried to tell this guy, well, nuclear physicist or mechanical engineer, something like that. He literally tried to tell the guy who's taking classes on statistical mechanics what entropy is and what it means. It was just funny. Anyway, continue.
That's why I'm hanging out with Immutable here, because I tried to tell Neff, don't use the second law of thermodynamics.
Well, Nephilim Free doesn't know anything about anything. I'm sorry. I don't know if you're friends with him or not, Sal, but Nephilim Free literally knows.
All right. So I figured I'd learn some real science here tonight. Sorry, Neff.
I see we're talking about integrals and
Yep.
integrals.
What we're now doing is we're determining the constant in front of this wave function.
Oh, fun.
Yeah.
Headphones off.
Oh yeah, always fun.
Yeah, Brandon said Sal told him. I heard him say it. Laugh out loud. Brandon has a good memory.
Who is Brandon?
He's one of my friends that I met.
Oh,
Came to Evidence and Reasons. So
what channel is this live on, by the way?
Cell Cordova.
yeah, this was a total accident. It's just one of my throwaway channels, and I was hoping no one would find us, but people found me.
People are finding us.
So what we've done essentially is we've taken the value of our wave function, or the wave function itself, squared it, and now we're integrating over a region 0 to L.
First off, Leo, I'm really, really sorry that I messed up, and
Hey, mistakes
I said
happen. Right?
everyone was on Eastern time, so I really was hoping you'd be with us. I apologize.
No, that's fine. So just because I'm curious, what has been covered thus far, and then what do you still want to cover?
Okay, so let me go back up to the top real quick.
Got to scroll through the notes.
So how the hell is this
I see Immutable is going. Well,
We
I
were
mean, you could say Yuki's going either Sean Carroll or
can I try to
Sal Khan.
summarize it for him?
Yeah, go ahead.
Because that would be a good way for me to recapitulate what I just been taught. So, if I'm gonna, can you unshare your screen, because I don't want to remove the wrong guy. So I'm gonna do a screen share, and let me see. We were doing.
Covered particle in the box for quite a while.
Yeah, because that's the easiest, because the solutions to the differential equation are easier.
Mm-hmm.
So we have this molecule here, the beta carotene, and so I'm trying to if I state this wrong, this is why I want to learn this.
Yeah.
Immutable, correct me. There's some sort of pi electron that can go from here to here. So it's like a particle in a box.
Yeah, it can go from the pi electron on the ring, so
From about right here, and it can float all the way out to here.
yeah, that's correct. So this pi electron that's trapped in this ring is allowed to donate to other carbons in that ring, and as a result, it will force some of those bonds that are occupied to also move along the molecule.
Right. So classically, so let me see if I can clip here. Classically,
Wait, hold on. Is this kind of relating to why did I just entangle? No, not entanglement. Tunneling.
Not
No.
quite.
Okay.
Not quite. This is Schrodinger's equation in a simple example. So classically, if we had a particle, it would be incorrect to say that the electron that is moving back and forth in here, and it's really not moving back and forth. Remember, it's just kind of spread out. It's classically, if we modeled it like a marble, we'd be having it bounce back and forth like between the two ends, and it would look in classical physics like diagram A here. But what it's really doing is there's a probability that it's going to be. That's what we're trying to solve, and I wish they didn't have it dynamic, because that just makes it's a little bit different. So
I'm assuming you're doing 1D, one-dimensional particle.
Yeah, we are.
Yeah.
Right. So that's why I wanted to share kind of the one-dimensional case, and then so I wanted to, because when some people see the particle in a box, it seems so abstract. It's kind of nice to see a physical example where we have an electron in a kind of in a physical box. Now, it's only an approximation with the beta carotene. So then Immutable has been walking us through how Schrodinger's equation would predict the probability of finding that electron inside that beta carotene.
After I'm done for one minute.
And I wish when they were teaching this to me that they said, just consider this beta carotene model. It wouldn't look so abstract. You can actually kind of visualize something physical, because when they just throw this particle in a box, I'm just like, what is this? So
Yeah.
anyway, go take it away, Immutable. So that's a real quick summary of what we were talking about. So now he's trying to show how you could actually work the probability of finding that electron in the beta carotene, which is the particle in the box.
Yeah. So for this equation,
So you need to share your screen again. So thanks, Immutable.
yeah. Let's see, where in the hell are we? Okay, there we go. Back. Good.
Okay, I'm going to add it to the stream now.
Good. So we need to solve the square of our wave function integrated from a point 0 to L. I won't bother in showing how to integrate this sine squared function with respect to x. But what I will say is that, just rewriting it, k times x. I will say that this conveniently evaluates to
1.
it
The definite integral has to be equal to 1.
right. And in this case, it turns out that this will just evaluate to x over 2, evaluated at 0 to L, which is L over 2 minus 0 over 2, which is L over 2.
I didn't know that.
Yeah, the reason for that, actually, is that the sine squared of kx can be expressed as being 1 plus the or rather, 1 minus the cosine of 2x over 2. And this actually needs to be k. This needs to be 2k. Yeah.
All right, I got it. All right.
Yeah.
So when you throw in all the pi's and all, it'll. Okay.
Yeah, it'll vanish.
Okay.
And so what's important now is that this means that b squared times L over 2 equals to our is in fact equal to our
Quick question. L is the length in the well in this scenario, I believe, correct?
Yeah, L is the length of the box or the well that we're considering.
Yeah.
And that means that b squared is 2 over L, or that b equals the square root of 2 divided by L. Good. Now that we have a value for b, now that we've normalized our wave function, psi is just simply the square root of 2 over L times our function times our sine function times our sine function of k times x, where k is well, actually, in this case, actually as well, right? What we knew about, let me move back here for a moment. So we knew that our k value, which was this, had to be equal to n pi because of the initial conditions placed on the wave function. And so recalling that, we get a very simple expression for our function, in that our particle in a box, the solution for it will just be square root 2, sorry, I wrote that incorrectly. This is the square root of 2 over L sine kx, but that is equal to the square root That's P divided by L times the sine of n times pi times x divided by L.
This is all
Bravo.
only vaguely familiar to me because I never worked through the infinite square well problem on my own. I watched maybe 2 videos on it, 3 videos, something like that.
Now, Leo,
so-
do you have Griffith's quantum mechanics book?
No, but I have Leonard Susskind's quantum mechanics book. I read parts of the 3rd edition of Griffith's book,
Okay,
but I
so
didn't read the whole thing.
The reason I wanted to, greetings, Gavin. Thank you to all our viewers here. If you look at Griffiths, the notation is just a little different than what you see here.
Yeah.
This would be in equation 2.28.
I don't know if Susskind goes through infinite square well. Let me go to the.
But if you have Griffith's
index.
book, I'm just pointing out the equation is 2.28. The notation is just a little different.
That's because he does infinite square well, and I believe it's part 1 of his book. I think it is.
Yeah, he writes it as square root of 2 over a, in fact,
Yeah.
and sine n pi a over x.
H. Wait, what the fuck?
Is that Susskind book the theoretical minimum book?
Yes.
Okay.
I don't know if he actually works through the infinite square well problem, because David Griffith's book it's not really a textbook, but it's more supposed to appeal to actual undergraduates taking the course, whereas this book is more just kind of like somebody like me, like a layperson just wanting to learn about quantum mechanics. So I don't know if he actually works through that. I don't think he does. When I read it the first time, I understood maybe 20% of it. I didn't recall the infinite square well problem, but I guess I can't say that he doesn't talk about it. I don't think he does, though.
But this is in fact our solution for an infinite square well, and that's easily the most simple quantum mechanical problem.
Oh, yeah, definitely.
In fact, it works for a lot of stuff. But I don't know if we want to go through the 3-dimensional one. Probably not, because that's quite a difficult little nightmare to handle.
Yes, it is. That much I can attest to.
But what I will say, to give you an intuition as to why we can only solve this in as a result of one particle, is for the reason that, keep in mind that this particle, right? So let me redraw the well.
So I probably can't. So I've got some questions about the infinite square well.
So let me use the book's notation A in this case. At the boundaries negative A and A, the energy here is infinite, right? Although, recall that this particle can be charged if it wants to be. That's no restriction. It doesn't have any influence on the particle's behavior. But let's notice something. That let's assume that this particle is in fact an electron, right? So let's assume that this is an electron E1, but that we place another particle in this box, E2. Well, what do we know about electrons or any charged particles? So it turns out that particles with a charge, in fact, have a very nasty property to them, that they have, in fact, the charge is spherical. So it distributes itself over the volume of the particle. But that becomes a problem. It means that since the electric field is infinite in terms of its range, and it grows dissipatingly small, but what it means essentially is that if we really think about this problem, what we're dealing with now is we have a particle E2 we have a particle E2 so we have a particle E2 whose electric field extends everywhere, but the strength of that electric field dissipates very rapidly. But we also said we have another particle that that also has an electric field, and and as it turns out to be the case, its electric field also turns out to extend everywhere as well. But notice something. There's going to be a point in time where the field lines, the electric field lines, for this particle, actually, that's not clever, where the electric field lines for this particle, right, so let me depict its field lines by using the red color for it. And the electric field lines for this green particle, which I'll denote in green, where these field lines in between, so in this area, you're going to have this issue where you have the electric field particle from the first one being interrupted by the electric field of the particle of the second particle. And that means, though, that the probability of finding, so the Schrodinger equation for this, so essentially it looks like psi double dot of psi double dot of x1 and x2 plus nu plus some potential energy times psi that depends on x1 times x2 minus some other function, which say we call it the interference between x1 and x2 equals the energy. Whoops, that's not quite good. Equals to the energy of particles x. Depends on the energy of particles x1 and x2. But the issue is we can't solve this. Because even if we could find a potential, that the potential for this wave function of x1 and x2, the thing is, so the strength of the electric field, it turns out, so the electric field strength as a vector is equal to K E1, E2 over R squared. So in fact, the interference for this particle, right? So the interference that's generated by the clashing of the electric fields depends not just on depends on this first radius and the second radius. So K2 equals K E1 E2. And for that reason, it's impossible to solve. Because we don't know necessarily, if we're just measuring probabilistically, we can't solve this because of these R squared terms. It provides us with a nonlinear, it would give us a nonlinear differential equation, and that is in fact, if not impossible, very, very hard to solve.
It can be approximated numerically. Is that correct? It's
It
just
can.
it's just not analytically tractable.
Yeah.
Okay. All right. So
I don't want to cover the three-dimensional
E1,
in a box. Please don't ask me to do that.
so E1, the equation E1 is the field from the.
This is just the charge of the first particle.
Okay, and then E2 is the charge of the second particle.
Yeah, for sake of brevity, we assume we have charge.
That's the Coulomb force.
Yes.
Yeah.
And okay, all right.
So we can't solve a 2-particle problem or 2-electron problem.
Well, and correct me if I'm wrong, Immutable. This is one part of quantum mechanics I don't know that much about. Isn't this where one might bring perturbation theory in to approximate a solution?
Yes, this is exactly where perturbation theory comes in play.
Okay.
Because you can consider with the time-independent wave function factors that are no longer linear in terms of that are just no longer linear, and that's where perturbation theory comes in handy. But yeah, so that's quantum mechanics.
For what it's worth, I heard that we don't really have a lot of solutions to Schrodinger's equation except for really trivial systems.
Yeah.
So we have to use
right.
We have to use kind of experiments to guess.
The only other solutions we have for so I'm not going to explain how these solutions are derived because honestly I don't have the patience for the multivariable calculus, and I'm also not that familiar with. I haven't taken multivariable calculus in like 5 years, so I'm not exactly up for it. But what I will say is that the three-dimensional Schrodinger equation looks like this. Times psi double dot. Well, yeah. Let me use times it's called the Laplacian psi minus mu of psi equals v of psi. And for those wondering what this thing means, so it's the partial, so it's the second derivative with respect to x,
And
plus the second derivative with respect to y, plus the second derivative with respect to z.
and what just for reference, that is equation 4.8.
Yeah.
Second edition.
So this is the three-dimensional equivalent of the Schrodinger equation. You have to make so by means of polar substitution, you generate a different form of the Schrodinger equation, which, let me Google that.
Does this new form have the imaginary unit in it?
Let me see.
No, it has something a bit uglier.
I'll get it for you, Immutable. Laplacian in polar coordinates.
Oh, found it. There we go. Yeah, this is quite an ugly function. So under polar substitution, so under...
How about I show it? Do you want me to show it?
No, I'll just write it. It's an ugly ass equation, but it's worth mentioning. So this actually turns out to generate an equation which looks like this, which is negative h bar squared. This becomes equivalent to negative h bar squared over 2m. And this new function will be in terms of a variable r, which is a radial some distance on a sphere, and it depends on two angles, theta and let's see what they call the other one, phi, naturally. And that's annoying. It's choosing to disobey me. R, theta, and phi. And this actually gives us an ugly mess of a thing. It gives us that this is equal to negative h squared over 2 mu times 1 over r squared sine theta times sine theta times the partial with respect to r of r squared times the partial of psi with respect to r plus the partial of theta times sine theta times the partial of psi with respect to theta plus
Why does this look vaguely familiar? I don't know.
You'll see it in electromagnetic theory.
That's probably why.
plus 1 over sine theta again times the second derivative, actually, with respect to phi squared of phi.
You said phi squared, right?
Phi, yeah,
PHI.
phi, psi, yeah.
Okay.
Psi, actually, in this case. Sorry. Psi is our... I hate this. Psi is our wave function. Phi is one of our polar angles.
Mhm.
Sci-fi.
Partial phi squared of psi. And I know, we're still having fun. So, this thing's going.
This is why people suffer through electromagnetic theory. All the equations are just monstrously large.
Yeah.
Yeah.
They're
Plus-
just
Yeah,
I've often been told that quantum electrodynamics is actually not as, I don't know if hard is the right word to use, more so than maybe like rigorous as classical electromagnetism.
that's news to me.
Sal, you took quantum electrodynamics, QED?
No, I did not.
Oh, thank God. I was like, Jesus, hell, you're a trooper, man.
I don't know if they teach that as a class, more so that you learn about it generally in it, like advanced quantum mechanics. Well, actually, probably more advanced quantum field theory courses, quantum field theory 2, quantum field theory 3, potentially classes that teach the standard model. But you're also learning just gauge theory in general, and you work through different gauge theories: U1, SU2, SU3, Higgs, all that.
I have a version, interestingly. I have a textbook on quantum field theory. I don't understand shit about it.
Is it by Mark Srednicki?
Let me check.
Because I have heard that one is a really good book. I actually have it as a PDF on my phone.
Let me check. This is a good question. Quantum field. Come on.
Uh-oh.
Just for reference, then, that last equation that Immutable wrote is equation 4.14 in the second edition of Griffith's.
Let's see. No, that's
Oh,
not
Matthew Schwartz. Okay.
No, that's not the right one.
Oh, no, never mind then.
Let's see. Is this the right one? Tom Lancaster? Yes, here it is.
Okay. That, by the way, that'd probably be Lancaster.
Lancaster.
I actually don't know if you might actually have heard his name. I would assume that'd probably be pronounced Lancaster, but I could be wrong.
Fuck if I know. But yeah, this is a book I have and that I don't understand shit about.
I don't know if I could pull up.
Which one is that?
Quantum Field Theory for the Gifted Imager, excusez-moi,
Oh, Lancaster.
by Tom Lancaster and by Stephen J. Blundell.
I might not actually have it on that particular phone. Let me Google it and see what I get. Quantum Field Theory, Mark. There we go. Mark Srednicki.
Yeah, this book starts off pretty basic if you know some differential equations, then it goes fucking insane.
Yeah, a lot of group theory and Lie algebra.
Lie algebra?
Yes, it's a form of abstract algebra, I do believe.
I think it's Lyle.
It's Lie.
Another thing I
It's
don't know.
definitely
Lie?
Lie.
Really?
Yes, because it was developed by Sophus Lie, who was. I don't know. I don't think she was French. Let me find out. Marius Sophus. Oh, is he? Marius Sophus Lie. Why did I think it was a female? Norwegian.
So what you're telling me is that I have to learn abstract algebra to understand.
And group theory. Well, at least group theory if you want to go the route of gauge theory, because group theory is what gauge theory is essentially built upon mathematically.
Isn't group theory basically abstract algebra in a nutshell?
I think it bases itself off of abstract algebra, but I think there's some more concepts to it.
There
Quantum
a
mechanics.
really good series on group theory by it's this English guy. He does all kinds of biochemistry stuff too.
Oh,
David. I forget what his name is. And also Steve Roman. Is that linear algebra book you got?
Yes, group theory is essentially a branch of abstract algebra.
Yeah. It's kind of the first thing you will run into in abstract algebra.
It's the study of groups in an algebraic sense.
When I took abstract algebra, I said, I'm not going to be a mathematician. Yeah, it wasn't so much the math, the electromagnetic theory. The math was actually harder, but the problem is you have to really love.
You really got to love math and hate your brain cells to do that.
You got to hate the brain cells in order to do calculus.
No,
there
you-
wasn't anything.
Calculus is not that hard, though.
Yeah, but the
Calculus
thing
really
was, in
messy.
abstract algebra, it didn't tie to anything in everyday life that you could experience. You could see calculus in everyday life, because you have slopes and stuff, and it's like, yeah, a little occasionally you do integrals, but some of the stuff in abstract algebra was just so far removed.
Well, your clock is
I
based.
fail to understand how I really fail to understand how abstract algebra is so abstract of a fucking field, yet it managed to be kind of central to a lot of fucking shit.
Yeah.
Like
Especially most of the stuff that underlies the whole of reality.
it has to do with cycles.
Oh, that just makes me laugh. I'm sorry. It's so abstract. Now let's explain particle physics.
Yeah, it's like
I remember being in the cafeteria with my classmates, and they just wouldn't stop talking about isomorphisms and homomorphisms. And I'm just like, okay, guys,
I know the term
this is
diffeomorphism.
not the stuff I would talk about, but they just wouldn't stop talking about it, and they'd be describing all these systems, and they were just so fascinated. And just like, yeah, this.
Oh, okay, yeah.
To sleep, guys.
I think the appropriate question I'd be asking is, how much cocaine did you guys take, and where can I find some of it?
Oh, who's ready for group theory?
Well, actually, it's better to take acid if you're doing group theory. I'd say cocaine.
I'd say mushrooms, not acid. Acid's going to send you too far out. Mushrooms will send you out just far enough.
This channel does not condone.
If you're taking group theory, be sure to bring mushrooms and be sure to give me some. Because
Yeah. Oh, it's going to suck when I have to do group theory on Brilliant. I tried earlier this week to just kind of jump into it and just kind of, get my feet wet, see what it's about. I was in there for about 10 minutes and I failed like pretty much every question they asked. I was like, I hit the back button. I'm like, nope, we'll try this later.
Group theory. Oh.
Yeah, you get all hyped up, and then group theory comes back and is just like, sit the fuck down. You're not sit down. Sit the fuck down.
Yeah, you thought you understood addition. 2 + 2 is actually 0, fucker.
Yeah, pretty much.
Great.
And Sal is trying to keep this channel homeschool friendly.
I don't know. He invited atheists to the channel though, so I don't know.
I know.
Group theory comes up and says, "Are you ready to learn me?" And you're just like, "Fine, but I'll have to relearn everything that I already thought I knew again, won't I?" And he's just like, "Yeah, you will."
Yeah, basically. Yeah, pretty much.
Who is that guy that did the series on group theory? It was wonderful.
The thing is, too, it's like abstract algebra isn't even the hardest thing in the world. If you look at things like string theory and then algebraic topology and stuff, which basically is string theory on crack.
Yeah. Differential geometry is harder than it sounds. I wouldn't say it's the hardest one out there, but it's harder than it sounds.
I'd say classical mechanics was the hardest class I took. Differential geometry was a little easier than classical mechanics.
Statics and dynamics.
How is it easier?
That may sound surprising because you think, classical mechanics, but the math, that was at least the way the professor taught it from Goldstein's mechanics book. It just about killed me. And I said, I'd take
Goldstein,
any day.
that's your use.
Yeah, that puts everything into context for a second.
Yeah, there we go. That'll explain it.
Goldstein's mechanics. I just like, give me quantum mechanics or general relativity any day. I just said, classical mechanics should be easy. That's just old hat. Just like
general relativity, at least for me, because I tried it, was pretty like it bends you over. Let me just put it that way. Well, it bent me over.
Oh yeah,
that is differential geometry.
Yep.
And
but a lot of vector calculus too.
But
yeah, basically.
But still to this day, I said the hardest class I ever took in my life was classical mechanics. Mathematical physics was just below that, and then maybe below that was plasma physics, at least from the professors that I studied it from.
What exactly is classical physics, at least the way it's taught in university?
Isn't that just Newton's formulae, like motion and stuff like that?
Well, there are reformulations of it, like the Hamiltonian and the Lagrangian. So there are problems in dynamics where we wouldn't take the original formulation of Newton and we'd cast it in terms of Hamiltonians and Lagrangians because it seems to work. And then if you look at it in the Schrodinger's equation, there's the Hamiltonian operator.
Yep.
So if we ever went to Dirac notation, you'll actually see the H operator.
Yeah,
that's a quantum version of the classical Hamiltonian.
Yeah, the time dependent Schrodinger equation has H hat in it. H hat psi is the first bracket. I believe is that just the first bracket? I think it goes H hat psi is equal to IH over the not over. Fuck, I'd have to go into my notes. I thought I had it memorized. Maybe I don't.
But I was pretty impressed there, Immutable. You're spouting some of this off from memory, I could tell.
Yeah.
Oh my goodness.
Oh no, I got that wrong.
Oh my goodness, you were just spouting the general solution to the one-dimensional Schrodinger equation. It's like, yeah, I don't memorize that.
Yeah, I remember having to solve it, and I was like, yeah, I'm going to devote this to memory for a long time, so might as well.
I used to have time-dependent Schrodinger memorized. I just haven't recited it in so long. It's H hat of t psi of t is equal to IH by the partial derivative with respect to time psi of t.
Yes.
Yeah.
And that's better than my memory.
I can give you the Lagrangian density of the standard model, too.
God, we'll be here all day.
No, well, the condensed version.
Oh, thank God. Okay. I'm like,
Negative
Oh,
1/4 f
alright.
mu nu f mu nu plus I psi d slash psi plus psi I y I j psi j phi plus the magnitude of d phi. No, not d phi. D mu psi squared minus v of phi. I think it
Yeah.
goes electromagnetism, weak interactions, strong interactions, Higgs. I think that's the order. I could have that wrong though.
Are the rules of mathematics both prescriptive and descriptive? Well, they're not prescriptive. Abstract algebra kind of throws a wrench in that one.
Yeah, the thing with math is math does not tell reality what it's supposed to do. It's something that humans made up to describe what reality does.
Oh, and for what it's worth, the debate between Nephilim Free and Jordan is still going on.
Mhm.
And I offered to do a after show that's called the Dumpster Fire Open Mic.
If you want, you could. David Neff has an after show set up. You could just join that. Nephilim Free's already said he's already told David he's going to be there. So me and Neffy are probably going to be having a pretty good discussion on cosmology because he doesn't know anything about it.
Oh,
Okay,
wait.
guys.
Everyone's going to the David Neff show channel. Okay, then I won't have to worry about hosting.
I also invited both
The open mic.
George Bond and Redefine Living to join, but George Bond might join the voice chat. I already know RD won't because he's a coward.
Who's RD?
Redefine Living. I'm sorry, I don't know if you like him or not, Sal, but that guy
I do.
is kind of a coward.
It's hard for me not to like people.
Guys, I put a treat in private chat for you. It's this guy. I don't know what the hell is going on, but he keeps changing the name of his channel.
A treat, buddy. This is not a picture of Amelia Clark. How is this a treat?
No, it's a treat. It's he calls himself Elliot Nicholson now. He's had several names, but he does wonderful stuff on biochemistry, and he does stuff on cancer and just a million things. But he does group theory. And he
I would recommend if you're going to go with group theory, go with 3 blue, 1 brown.
no, this guy is much better.
Probably not.
This guy's
So how come 3 blue, 1 brown is a bigger channel?
I don't care. He's
Better.
they don't know what they're doing compared to this guy. So
Yeah.
check him out.
Have you watched the video that I'm even citing? I haven't.
I have.
I watched that. I watched their
Group
video.
theory and YL
They look very good.
808-017-4247. I don't even know what the fuck number that's supposed to be.
All right. So, would you guys like to reconvene a talk another time, or do you want to continue with?
I think we need to get.
We didn't even touch Dirac notation, actually.
Yeah, I brought my book. I was ready to go at 9:30. I'm like, here we go. I get in here, hour and 19 minutes. I'm just like, what? Immutable's in here writing shit down, going off, and I'm like, what?
Yep. Yep. I know. I'm horrible.
In his image, asked me, can Sal actually name someone he doesn't like? His name is Daniel Carnes, and he did something that threatened my mother's welfare. That crossed the line. I said, God, just please take care of him. Next thing I hear, he's dead. I was happy.
Well,
I was actually happy that someone was dead. I said, he got his comeuppance, because you don't do that to someone who's a total innocent bystander. I was just so livid. That would cross the line. Someone does something to someone I love. You'll see another side of me that's not so nice.
I danced to the guy.
Immutable. I did have a question for you, if I may. Do you know much about the Dirac equation at all?
Oh, Jesus. Found out.
Dirac.
You remember Dirac notation. That is the question of the day.
The Dirac equation is just the way that I've been told is it's like the Schrodinger equation, just with special relativity, but it's not really like. I mean, it kind of is like the Schrodinger equation, just within the realm of relativistic QM more. So I didn't know if you knew much about it, because I actually don't know all that much about it and stuff like that. And I didn't know if you did.
Ask a physicist. They lost their mind a while ago. I still have mine.
Immutable, since you're the one that's been so generous to talk with us, do you want to continue, or do you want to do it another day, or can you tie us to the Dirac equation, what we just learned in the Schrodinger form?
Yeah, can you tie that to the aromatic ring, perhaps?
Not really, because
or the Pauline beta carotene. Can you?
No, because the issue is that electrons, orbitals, live in 3-dimensional space. and
Yes.
they have electric fields, and that's quite annoying because
That is annoying.
benzene rings don't look so pretty because electric fields, when they clash with each other, kind of fuck around with the position of where that electron's going to be. But somehow life finds a way.
So, what would you like to do? By the way, thank you for really walking us through this.
From what
And,
I understand,
I just want to say you have my admiration that you're able to just write quantum mechanics almost from memory, and that you even knew some of the Laplacian polar coordinate in polar coordinates. I would not have known that. A lot of professors would just let us bring cheat sheets to the exam because they just thought it's kind of mean to make us memorize. Because if you get one term wrong, you're toast.
oh yeah, I would still bring cheat sheets to the exam because, oh yeah, trust me.
Do they actually let you do that in college? I've heard that in some senses they kind of let you cheat on tests.
Yeah, it's because certain equations
Cheat, I should put that in quotes.
Well, the reason is some professors wouldn't know it from memory either. I studied under really smart physicists, and you could see them. That's like, okay, let me make sure. And drawing it up on the chalkboard, they're always double checking, because it's easy to get, like, if you forget to put a square term or this, or you interchange something, everything just falls apart. And so I think they're kind of sensitive to knowing that. And I think a lot of professionals anyway, when they're trying to solve things, they just put it in Mathematica these days. They're not going to try to solve a lot of things by hand.
Yeah.
That's just too brutal. So immutable, whatever, what would you like to do?
I'd like to cover like the linear algebra aspect of it at another time.
I actually kind of agree with that, only because I do want to, and I don't know how much longer the debate is going to go, but I do want to get to David's after show when I can. And it's not the linear algebra of Brock-Tat notation isn't like super. It's really not that rigorous. I personally don't think linear algebra is really that bad.
No, there's just a lot to it.
Yeah. It's got a lot of meat. There's a lot of meat there, so to speak. Which it makes for a good meal, though. So
Yeah, I mean, the thing is, like, with matrix mechanics or linear algebra, sometimes it's called, it's just there is so fucking much of it. Like, there's like LU factorization, LDU factorization. It's like, oh, gosh. You can do all sorts of weird things with matrices that are just like, okay, why?
And so so the linear algebra is tied to Dirac notation. Is that correct?
Yes.
Yes, and it's because if we have a system of more than one equations that relate these phenomena to each other, what we want to do is we want to use the language of linear algebra.
No. I'll be in here for a while.
So,
well, if she...
So with it, so maybe for next time you could show us how the Schrodinger equation fits into the
I'd have to...
Dirac notation.
Yeah, because
could you do it for the particle in the box to show us like how we would do it with Dirac notation, or is that too trivial for Dirac notation?
It's too trivial because Dirac notation, if I'm recalling it right, let me see. I think Dirac notation.
What was the question?
Oh, did you ask something, Leo?
No, I asked what the question that was asked was.
I was asking, could we take what we did today in Schrodinger's equation? Could we reframe it in Dirac notation just so we could see the connection?
And
I asked, is it too trivial a system that we wouldn't use Dirac notation?
Well, the time-dependent Schrodinger equation is written in that particular notation. At least for the most part. I don't know if it's fully. I know there's Ketz in it, but I don't think it would be that trivial.
Can we go to the top and figure out what operators are? And
well, it depends, because an operator in quantum mechanics is just so a function takes a number and spits out another number, as we all know. An operator takes a function and spits out another function. So it's like a function on crack. That's what an operator is.
Or like a functor in category theory.
You're a functor.
You functor. Yep. We gotta train you to start saying functor when you're on sales channel. What is that?
You know, it's reasons like this that I have not studied abstract algebra yet, even though I have.
Well, this is why I'm hosting it on another channel. Just the FYI for just to repeat, I'm going to have a channel that's for homeschool moms and then channels like this where everyone can be more free.
You're going to teach them evolution and how evolution works. You're going to teach them how macroevolution works.
You want to teach it?
Why are you giving him?
I think people should hear both sides, but you have to clean up the language.
Oh shit! What did I just do? I fucked up.
I don't know if there's really two sides to it, but
What?
Leo, do you have a filter anywhere that you could buy? Could you buy a filter?
Yeah, no, I have an off. I have an off.
Well, I'm going to teach
phosphate, or is that the on switch?
You need the off switch.
What filter is this?
I don't know. I accidentally said the F word, and
Oh.
I know you're not particularly a fan of that.
Well, I accidentally say the S word a lot.
So, and if we do cover, just to ask, does anybody want to cover vector spaces first? Before, and this would be when we cover, or do we all know enough about vector spaces? Probably we do, I would assume.
Well,
I could use a brush out.
Because really, it's just like, you know, defining any particular space. They just have a different, their own particular set of rules.
I do remember a question on an exam in linear algebra, and I said it's the span of the basis vector, and I was like, Lord, I hope
That
answer.
That actually is. I mean, I personally wouldn't consider it a wrong answer. It might not be like the most rigorous or technical answer you could get.
Well, he gave me full credit. I was like, that was just a mark.
Yeah, I think there's 4 properties of a vector space. The 2 that I can only like actively remember are that it's commutative and that it's associative. Also, is there something that has to do with an inner product? I think.
Oh goodness! There has to be inner products. Okay, hang on. Mutable's putting something here.
Mechanics.
By the way, if anybody wants to kill themselves and learn abstract algebra, this is
You want to talk about killing yourself? Statistical mechanics.
no.
Yeah.
Statistical mechanics. I took it.
Statistical mechanics literally killed Boltzmann.
He committed suicide. Yeah.
Literally, it killed him.
What's the joke about that?
The one introduction in that book, it talks about all the people who were involved with statistical mechanics and that they had essentially died. Hold on, let me see if I can find it.
Aaron,
It's quite depressing.
Let's see.
By the way, if you want to be like all these famous,
Right here. Here it is.
Go
Thermodynamics and statistical mechanics. Introduction is 1.1. It's the introduction. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it is our turn to study statistical mechanics.
It's too bad we're laughing about that.
But it is, I'm sorry, it's kind of funny.
just like, okay, guys. By the way,
actually, I mean, if I could just say this, at least in my school, the hardest class was classical mechanics. Then the next hardest was mathematical physics from Matthews and Walker. After that would be probably plasma physics. Then the rest were hard. Statistical mechanics, at least the way they taught it from Pathry and Beal, was not that bad. It actually was pretty compelling. I thought I was actually pretty fascinated by it.
So I want to make a
that would be
statement.
one of the easier ones, at least from that. The hard part wasn't the math; it was the conceptualization.
Yes, I was just about to ask you, or really make a statement.
The math wasn't hard. It's like what's entropy, and then you have the classical version, the Clausius formulation, with the integral of whatever it is. What is it? dq divided by t or something. See, now I'm embarrassing. And then you have the Boltzmann formulation, which is
S equals Boltzmann constant times the natural logarithm of omega.
The logarithm of the number of microstates. And then you'd actually work through it, but it wasn't that hard, except for a couple problems that the professor assigned, which no one solved. And I spent 2 days on it and I still got it wrong. he said, the answer is in the back of the book.
So, but I did want to make a statement, and Immutable can mention about this too. But to both of you, Immutable and Sal, because I have heard and in some ways kind of seen on my own that it isn't really the math that makes it hard. It's whether it's the ways in which this math can really be conceptualized. If it's easy to conceptualize it in the real world, if you can think of examples where this math can easily be applied, it's like, okay, that makes sense. Whereas if you're learning math, but it's really hard to kind of conceptualize where this would work or what you might describe with this, that makes it a little bit harder. Would either of you two consider that true or not really?
Yes, this was very much like, well, what sort of physical problems does this solve? The only one where it tied to anything that is familiar to even any science is the equation for the Gibbs free energy. And it's like, well, you didn't need to go through all that statistical mechanics to actually just memorize that equation, but they showed how it was built, how they, from first principles, how they built the equation for the Gibbs free energy, which is used a lot in chemistry. It's just like, that's so much. But then there was a lot of classes to show that. And then kind of with the quantum mechanics here, it's in chapter 4 that they show how you used Schrodinger's equation to create all these 3-dimensional orbitals. And that's where you use the Laplacian to, of course, you don't solve it from scratch. They would appeal to mathematicians who solve those tough problems. But then it's like, well, after it's already solved, you don't really have to rework the math because it's already done. And then I would say the same, definitely, we don't use general relativity for much engineering. I mean, you'd need it to, if you're going to build a GPS system. And so I was talking to a PhD in physics just recently. He's going to come on my channel. He's a creationist like me. And he said, yeah, Sal, so I said, what classes did you take that you actually used the physics for kind of everyday problems? He said, not much, we really never use statistical mechanics. I'm like, yeah, that's the truth. So what these classes do is they teach us how we derived all these formulas we used, like the Gibbs free energy. But after that, you don't use it for anything kind of like, except for really specialized applications. So just like when we solve the orbitals, it's like, okay, we just you just look in a book and you just have all the pictures of how they're shaped, and that's about it. But so a lot of the graduate stuff is actually kind of seeing how is more of a historical look of how all this got developed. And so that's what's a little bit frustrating, is then I studied all this and it's like, yeah, I kind of missed out on all the elementary stuff. Like I haven't still taken organic chemistry, and I want to go back, even stuff with general chemistry. I want to go back and learn. I was looking at equilibrium equations and the concentrations. So I'm just like, oh my goodness, this is bad. Or the Michaelis-Menten constant. It's like, there's just so much I want to go back and relearn because it was shoved down my throat so fast. I have good short-term memory, but then it's gone after I take the exam.
Yeah.
Hey, as long as you pass the exam, right?
Aced them.
I did actually find. What's up?
I have another treat.
I did.
One of our clients is called Cookie Cart, and they deliver you a box of baking bright futures. They deliver you this box with about 20 assorted cookies in it, and you can get them weekly. That's a treat.
It's interesting. By the way, I should say I did
diabetes.
There are actually, at least Leonard Susskind lays out here 7 rules of a vector space. It's actually not hard at all.
Well, the reason I brought that up is because we were talking about an electron in a box. Think about a cookie in a box.
What about it?
Think about something pleasant, like an electron. It's a simple little thing.
Cookies are better.
Cookies are not
tired.
Cookies are not even close to simple.
So did you? So the question was, did anyone want to review? I would be interested in reviewing linear algebra with someone.
Yeah.
Yeah, I'm going to need to actually. So come to mention it, I'm re-enrolling actually to go back to school to do biotech because I need to get into the industry program, biotech certification. And one of the courses I will be taking as an elective, believe it or not, are discrete mathematics and linear algebra.
Yeah.
You know what? I love discrete mathematics for a different reason. It's very good if you want to play in casinos.
I have heard that before.
Probability and the pigeonhole theory, you're pretty much good to go.
What you need to know about linear algebra is Gilbert Strang from MIT.
Okay.
His books
Very
and
good. Although,
So I'll write to you guys if I host a class on. So just to announce them, I have to take care of Mom. So Carrie,
I got to take care of a pizza.
well,
Okay.
you want to share the pizza, Michael?
I got a pizza from Domino's.
I do know that they're at the Q&A on the debate, so I'm assuming probably 10:45, 11 o'clock is when David will have his after show open.
That's when he announced it on the email.
What?
So, that's when he announced it on the email earlier today. No.
Are you guys planning on joining? Because it's going to be fun.
I'm
I'm going to eat pizza and watch something.
not sure if I have enough brain cells to tolerate now.
What day is it?
Oh, yeah, you do. It's Friday. It's
Why?
Friday.
How did it get to be Friday?
Fritty.
I've abstained from alcohol, but that might have to change.
Me too.
The stream.
I had an interesting discussion with a guy on AA on the channel today for an hour and a half.
I watched that for a bit. Yeah.
Did you? Yeah.
What was I going to do? Oh, yeah. MIT open course wave statistical mechanics. No linear algebra. Watch me some lectures. I think I've watched a couple already. I need a.
Have you found Gilbert Strang, MIT?
Actually,
Wow, I am so fucking dumb. I've been calling it open course wave this whole time. It's open course where.
Oh no. Well, that's good.
Holy shit, that's bad.
Anybody can make that mistake.
Oh shit. Open course where open course wave. That doesn't even make sense. Wow, I'm dumb.
Gilbert Strang is still going. I think he must be
Well,
like
Gilbert Strang, didn't he? Yeah, he teaches at MIT, doesn't he?
he. I thought he retired and he started doing YouTubes, but now he's got another course. I think some other linear applications of linear algebra. I think is his latest. But he's got a twitch in his eye, which is drives you crazy watching him.
So,
But God,
as we were talking about last time. That's more than just an eye twitch, though.
yeah, it's more than an eye twitch. That's
you know, it sure as hell beats listening to Kip Thorne. God,
Who?
guy.
Kip Thorne.
Kip Thorne,
Who's that?
very famous cosmologist who deals with black holes.
Yeah.
Oh. Kip, K-I-P.
Yes.
Thorne, Thorne.
There he is. Oh my! Does he have a twitch or a tick of some sort? He got it. Does he have a tick?
Well, he has a stutter that will wake the dead.
Yeah, that's pretty good. Here we go. Warp side of the universe. Kip Thorne at Cardiff. Something.
What do we have here? I suppose I could do some linear algebra from Khan Academy. That's always a good place.
Let's see.
Elimination with matrices, multiplication and inverse matrices. Why? I don't get why they didn't just call them matrices. Like, come on. For
Matrices?
fuck's sake.
You mean matrices?
No, yeah, but I don't get why they didn't just call them matrices. Like, why not? Why did you have to change X to a C? Just keep the fucking X.
It just doesn't look right.
Or they should have just called matrix a matrice.
And other secrets
A matrix.
in the universe. I don't know.
Transposes, permutations, spaces, R to the nth.
Ooh, the sparkling ice has electrolytes.
34 lectures. That's not bad. Wait, is this the same guy? Wait, hold on. Is this?
Are you looking at the group theory link, or are you
No.
looking at Gilbert?
Oh no, yeah, no, yeah. This is Gilbert Strang. Yeah.
Yeah, Gilbert Strang. He's amazing. I have one of his textbooks, I think. I'm not sure if it's the most recent one, but I forget which one. Yeah, two of his textbooks.
Yeah. What the fuck is his name? Why can I not think of it? Not Hunter Bailey, but the other guy that I think he lives in Australia. That does Sentinel Apologetics. He also recommended Gilbert Strang for linear algebra.
Yeah. Gilbert is the master, absolute master. He got kind of famous for his YouTube series.
I wish I could just be like just be that good at math. It would be fucking great. I'm sure, honestly, I could be if I really, really dedicated myself to it, which if I ever plan on going to college, I'm going to have to. Funnily enough, I had a dream last night that I was at university in a quantum mechanics class, and I was actually doing pretty well. So I don't know, maybe that's a sign. Maybe God is like, I need you to go to college. And it's like, yeah, well, let me get accepted to Harvard, and it's a deal.
If I had a do-over for my life, I would start with mathematics in probably 5th grade. And I don't know. I could have got to do it.
I'm trying to, God fucking damn hairs. I'm trying to blow this hair off my fucking screen.
Okay, so.
I just, I have to go back and take care of Mom, but I just wanted to say if anyone, I may be looking to make YouTube videos to teach things. It's actually a great way for me to relearn things. So I try to build out content for one of my channels as well as teaching myself, because I don't know, the process of drawing up diagrams and looking up examples, it's very helpful to me personally. Yep. So
I second that.
So I'm just gonna throw that out there, because if the Dirac notation needs some understanding of linear algebra, then I need to refresh on that.
All I can say is, honestly, as long as you know what a vector space is, as long as you know what vectors are, and I'm assuming you know what the dot product is, that's essentially the inner product is just, I believe, the dot product for vectors with complex numbers in them.
Yeah, I've done that. It wouldn't hurt to just be more familiar with it. I mean, obviously, in classical mechanics, you're just using it, and then some tensors can be represented with matrices, but not all of them.
Yeah, so, matrix multiplication would be another thing I would.
Yeah, so this would be a good thing, and just as a refresher. So I can email you, Leo. And actually, this is how this all started. I started emailing Leo, and then he said, "Can I invite me Immutable?"
Yeah,
and
I was like, I'm not as up to speed on the math as Immutable is, so we should probably have him there too.
Yeah, I remember some math, so I guess I'm good for something.
On May 5th, Gilbert Strang did a new video called "A New Way to Teach Linear Algebra," and he's kind of rebooting his whole method. And so he's still active, and I'm not sure if he still teaches at MIT. It looks like he does.
Download.
He's a fascinating guy. Born in 1934.
Holy shit, that dude is old.
86 years old, and he's still doing videos. Awesome.
I've got actually Introduction to Applied Linear Algebra. This is a textbook. I can't remember where it's from. I downloaded it as a PDF.
That's
How many times do I have to fucking double click it to open it? Vectors, matrices, and least squares. Department of Electrical Engineering, Stanford University. Ooh.
Oh no. I want to save Gilbert.
We got vectors, linear functions, norm and distance, clustering, linear independence. Part 2, matrices. Matrices, matrix examples, linear equations, linear dynamical systems, matrix multiplication, matrix inverses. Part 3, least squares. Least squares. Least squares, data fitting. Least squares, classification. Multi-objective least squares. Constraint least squares. Yeah, this just keeps going. Okay. How many pages we got here? 455 at least. At least.
MIT OpenCourseWare. Finding anything on MIT OpenCourseWare is horrible. Because they have so much of it.
Type in MIT OpenCourseWare and then whatever I'm looking for, and then it brings me to it, and I go to the video lectures part, and then I click on whatever particular lecture I'd like to watch.
will I do that? MIT Gilbert string.
Ah, the debate is over, so I should be getting a notification from David shortly.
Here we go. 1806.
Oh
Gilbert
shit!
string lectures at MIT.
I forgot. I also downloaded Introduction to Functional Analysis and an Introduction to Statistics and Data Analysis for Physicists. That is not probably actually that one wouldn't be so bad. Functional analysis, I don't know how well that one I've heard can be a little hairy.
Hi, this is the first.
Okay. Downloading some Gilbert.
Banach spaces. Immutable. What the fuck is a Banach space? I've heard that. I actually don't know what it is.
Banach
The only
space.
time I've heard the word Banach is when it refers to Banach-Tarski paradox.
Okay. Was it spelled Banach?
Yep.
Yeah.
Okay,
Yeah.
probably the same guy. Normed spaces. So I'm assuming a Banach space is a normed space.
Algebra?
It can be infinite dimensional.
I will eventually hit abstract algebra when I'm immortal.
What was the name of the paradox you said? The Banach what?
Banach-Tarski.
Okay.
A complete normed vector space.
Okay. So yeah, it's just an okay.
Banach space is a vector space with a metric that allows the computation of vector length and distances between vectors.
Okay. Okay, this really isn't bad. This is really just about a lot of just spaces, I guess. Well, it's functional analysis, so that's not a surprise.
This abstract algebra by Stephen Lovett starts out pretty simple.
It's actually short. Holy shit.
What's that?
112 instructional pages in this PDF book. That's not that bad. You could
Which
read
one?
this in a day. I can give you the link to the PDF. It's Introduction to Functional Analysis.
Oh.
Do you want it?
Yeah.
Copy. Paste. And it's gonna look like a weird because it's a PDF.
PDF, right.
Nope, that's applied linear algebra. How many instructional pages are in this one? A lot, I know, because linear algebra. 448 instructional pages. What was the other one that I had? I had Introduction to Introduction to Perturbation Theory. I need to fucking learn perturbation theory. I just kind of get intimidated by it, I'm not gonna lie.
Said my file couldn't be accessed. Introduction to functional analysis. Who wrote it?
Daniel Daners. Daners, Daners. It'd be from the University of Sydney, Australia. And you should be able to find it as a good old PDF. How many instructional pages do we have in this one? I'm assuming probably a lot. Yeah, it's a lot. Yeah, it's depth. Oh my god! Holy fuck!
Daniel.
565 and oh my god!
Whoops.
Gotta love perturbation.
Daniel. How do you spell his last name?
Daners. I don't know if that's Danners or Daners.
Huh. Nothing by him.
Okay.
Your link didn't work for some reason. I don't know why. Let's see what he's got. He's got a book, but
to applied linear algebra.
Let me see.
Wait, I typed in the wrong name. What the fuck am I doing?
Introduction.
Functional analysis. Not analysis. Analysis. Alrighty.
School of Mathematics. Daniel Daners. Okay.
Right here. So if you
I
type
got
in introduction to you found it?
I got it, yeah.
It says the University of Sydney right there at the top of the very first page.
Yep. Interesting. I'm gonna have to go eat a pizza, guys.
Yeah, I'm gonna get ready for David's after show.
Zorn's Lemma.
Alrighty, I'm out of here.
Okay.
You should show up when you're done eating your pizza.
I should. We're at David's?
Yeah.
I'll
He'll
see
be,
how I
he'll
feel.
be
It's
right
like 11 o'clock and my, it's like past boomer o'clock.
Well, thank you
going
so
on?
much for joining us.
Yeah, no
So
problem.
I'll let you guys know if I set something up for matrix and linear algebra.
Sounds good.
Okay.
And I really appreciate you joining us. This was a very good and productive discussion.
Definitely. Had a lot of fun.
And I gave up watching the SFT channel just to be with you guys tonight. I skipped out on Neff's debate just so I can hang out with you guys. Just to let you know how much you guys mean to me.
Yeah.
I
Well,
gave
quantum
up
mechanics is
watching
important.
the SFT channel because I wanted to do root canal more.
Alrighty, guys, I'm out of here. Thanks for
All right,
having me,
take
Sal.
care, Leo.
Goodbye.
Bye. Steve.
Okay, later.